Start. Mic is off. Your mic is off.
Thank you, Helya. Welcome everybody to the presentation. I'd like to thank SkillShark and Rev Mechanics BIT for giving me this opportunity. So without further ado, let's get on with it. As you can see, the topic is motorsport engineering, an introduction to the science of speed. Now, what I'm going to cover in this session over the next 1 hour is just going to be a basic overview of how motorsport started, how the concept of racing came to be. Then we'll go through a bit of the different types of subsystems that are involved in cars and what you might need to familiarize yourself with if you want to work in that sort of field in the future. After this, I'll briefly talk about the different types of racing series that exist, and that'll give you a better idea of how to distinguish between different types of cars and what the performance differences and racing style differences are between these cars. And finally, if time permits, we'll go through a quick race engineering session. I'll show you a lap around the Le Mans Circuit de la Sorte, and I'll show you some data that I've slightly modified. Okay, so we'll start with a small introduction about myself. So I studied in SRM University. I did my BTech in mechanical engineering from SRM between the years of 2014 and 2018. And during that time, I worked in the Formula Student Combustion team of the university, Camber Racing. It was a great experience. I worked primarily in the aerodynamics department, worked on developing front wings, rear wings, diffusers, the underbody, and also some of the bodyworks of 3 different cars over the span of 4 years. I also had the opportunity to drive the vehicle during that time, and it sort of helped me hone my skills in driving, and it kind of helped me understand a little bit better about the performance estimates of a race car. And I also had the opportunity to work in team management in the final year that I was with. I was in which I was in the team. So this gave me an overall experience. What I'd say for anybody who's interested in Formula Student is it gives you an overall experience of how it is to work in a startup and potentially in a bigger company. So because of my love for race cars, I decided to continue studying. So immediately in 2018, I went for a master's degree in motorsport engineering from one of the most reputed universities in that field, which is Oxford Brookes University. So that was from the year 2018 to 2019. And I submitted my thesis around about a year back from now. So somewhere around September last year. And during that time, I also worked in Oxford Brookes Racing Autonomous and Oxford Brookes Racing as well. Because I mean, yeah, so I worked in that. Primarily, I worked a bit in business plan in Oxford Brookes Racing, and then when I shifted to Oxford Brookes Autonomous, I fully took on the role of leading the team and developing leading the business plan team and developing the presentation for the competition. So that's a little bit about me. I love racing. I've loved it for at least more than 75% of my life. So it's something really, really dear to me. So yeah, let's start off with what we'll cover today. As I told you, we'll go through a brief history of open wheel racing. After that, I'll give you an overview of the subsystems and the engineering involved. We'll go through some of the different types of racing series. Then we'll go through the race engineering session if we have time, and I'll show you a few extra videos if time permits. Finally, we'll conclude with a question answer session. Hopefully, we can wrap this up by 6 p.m. IST, and then we can have about 15-20 minutes of question answers. Okay. So let's start with the way in which motorsport started. How did everything start, and why did it start? Well, to start off with that, let's first. Sorry about that. Sorry about the delay. Let me just restart my presentation. So yeah, what I'm going to show you is a few of the cars that actually define racing history. So it all started with the Benz motor wagon, which is officially the first ever car that was built. And it was built and patented by Carl Benz. And as you can see, few technical hiccups, I'm sorry about that. Right, I hope you're able to see my screen now. Yeah, so let's start. So yeah, this is the Benz motor wagon. It was created in 1888. Now this car was actually, it had a very paltry 0.7 horsepower for the entire vehicle, and it was on a four-stroke engine. The top speed of that was 16 kilometers per hour. So that kind of tells you how slow the first ever car actually was in terms of speed. Now, what you see here in 1894, it's around 6 years later. So this is the DD-on engine. And this is really important in racing history because it was officially the first ever vehicle to win a race. So the official, so it was called the Paris Rouen Trial, which was basically a long trial. It was an endurance run, basically. And this well, technically car here traveled at an average speed of 18.7 kilometers per hour. Unfortunately, due to a few issues, they were disqualified because this technically didn't classify, it didn't actually count as a race car because there were two people involved. So since this ran on steam, there was one person who had to drive and another person who had to shovel the steam in. I think that's called a stoker. So because there were two people driving it, or two people involved, it was disqualified. But this is the first ever race car to win a race, if anyone asks. Right. So let's move on to the so let's move on to the next bit. So a few years later, Brooklands was created. Brooklands was the first ever racetrack. This was designed in Britain. Now, all the races that were held up till this point in 1907 were actually held in France. But what happened was British automobile giants wanted to get a head start and try to beat their French competition. But they had very low legal road limits, speed limits. It was around 30 kilometers per hour on the roads. So what the Brits decided to do is they decided to build a racetrack and a testing ground. And this is the first ever race car first ever race circuit to come into existence. Now it was used also. So there was a big gap in race, a small gap in racing during World War I, and this was actually used as a flight training zone during that time. Now, when did the actual real set of rules come into play? Well, it came in around the year 1928. So what you see here is the Bugatti 35S, which is one of the first ever cars in this new formula to win. And it's called Formula Libre, or the free formula. So the actual only rule that restricted cars in this era was a set of safety rules. Now, you might wonder why it's actually called Formula One. The reason is because it's not really any sort of equation or golden formula that solves the equation of building a race car. Here, formula refers to rules and regulations. So Formula One means that it's the top tier set of rules and regulations. It's tier number one, and that's why it's called Formula One. This is Formula Libre, which means that it's a free formula. And I think it's a French word. I'm sorry if I got that wrong, but it's called Formula Libre. Then there was a gap in racing, World War II from 1939 to 1945. And it was only in 1950 that the first ever Formula One race was created. This was the first ever winner of a Formula One championship. So the rules for that season was it just had to be a naturally aspirated engine of about 4.5 liters or a supercharged engine up to 1.5 liters. Um, Now, because of this, basically most of the cars were, almost the same in terms of engines. And at that time, it was the Italians that were really making great cars. So that's why this Alfa Romeo was on top at that point. But after that came a series of Mercedes dominance, where the driver Juan Manuel Fangio helped Mercedes dominate for a while. Unfortunately, just like how there's a Mercedes dominance right now, it was there in the beginning of the sport. However, in 1955, everything changed. So that was the year when the worst ever crash occurred in racing, and that was basically the Le Mans disaster. So Le Mans was actually an endurance race. It lasts for 24 hours around a circuit, and that's the circuit I'm going to show you at the end of this presentation. But what happened is there were a few safety issues, and a car actually launched off and launched into the crowd and exploded. That was a big disaster, and a lot of changes in the race circuit design came into play from that point on. What you can see here is basically the Mercedes that was involved, or the model of the Mercedes that was involved in the crash. However, this one didn't actually get hit. This was actually the winner of that race. But after that, Mercedes pulled out of motorsport for a very long time. So now we come to 1958, and what you saw right there was a Cooper T43 Climax, and this was the first ever rear-engine car. So up till this point, cars had engines at the front, which reduced the handling properties. It made the cars less. It made the cars stable, of course, but they also ran off track because of something called understeer. So what a mid-rear-engine car was basically the engine was placed behind the driver. What this did was improve the agility and handling of the car. And this is called oversteer. So after that, that's when all the teams started shifting to that direction. I believe, most teams shifted to that in that direction. Now, the next car you see here is a Lotus 25, and this was a big change in motorsport. So this was basically a car designed by Jim Clark. I mean, a car driven by Jim Clark, and basically it was designed by Colin Chapman, and he's regarded as one of the greatest technical designers in F1. And this car dominated for quite a few years from that point onwards. The reason why this car was really good was because it was the first ever monocoque chassis. Now, generally chassis are either tubular framed or monocoque. So tubular frame chassis have rods that connect, or rather tubes that are welded together to create a frame. Monocoque chassis are almost 3 times stiffer, and they also weigh about half as much. So these were really efficient, and this was basically a championship winning car and won almost 14 Grand Prix. We move on a few more years, 6 years down the line. This is the Lotus 49B. Now, this is the first ever time aerodynamics were formally introduced into vehicles. And as you can see here, there's a very modest front wing over here. It's more like a plank almost at this point, and just a really flat rear wing. Now, what aerodynamics actually does is it presses the car down onto the ground. So when you're cornering, basically it presses the car down. So the limit of static friction basically increases. So you have a longer limit for lateral loads before it starts sliding and kinetic friction comes into play. So that's where aerodynamics started showing its face in motorsport. So now we move on around about 10 years ahead. Before this, so what you have here is the Tyrrell P34. So this is basically unique in the sense that it has six wheels, as you can see here. The reason for that is at this point, aerodynamics started playing a really big role, and the front wing regulations changed. So they mandated bigger front wings. So in order to squeeze the front wheel into that zone, I mean, it wasn't possible. So they had to go with a really tiny front wheel, as you can see here. The problem with this is it doesn't provide anywhere near enough friction to actually keep the car stable through a corner. And as a result, they made it extremely small and fitted another one behind it. This car was very stable, of course, but the downside to having more wheels is you have more compliance, more movements in the car, and not to mention you also have an extra 2 wheels to carry with the car. So it's more weight for the vehicle. So because of this, these cars weren't that popular and they kind of died out over time. Now we move on to the next car. This is a Lotus 78. Now this was a turning point for aerodynamics. Now what this car used was something called ground effect, which means that imagine you have a car and it's close to the ground. So air gets accelerated underneath the car between the ground and the car. And what that does is it creates a suction. So in essence, what it does is it creates downforce. It presses the car down just like any other aerodynamic device. Downside to this is the sides of the vehicle are always open. So air would go underneath the car and push out. It would leak out, reducing efficiency. This car had something called a sliding skirt. It's basically was like it was, I think it was a cardboard or wooden plank that used to move up and down along with the road profile. It would literally be dragged on the road. So it's basically like a sealed tunnel at all times. However, this type of aerodynamic device got outlawed very quickly because of its insane power. And the reason why motorsport organizations try to restrict rules and slow the cars down is because if the car is extremely fast, it does become very dangerous. And drivers can only take so much G-force while going through a corner before actually being crushed by the force itself. Now, this is the Lotus 92. This is when the first ever official active suspension system was implemented. Now, active suspension, basically an active device in a car, is something that automatically adapts to external inputs and helps the car in very simple terms. So an active suspension is a suspension system that has either active dampers or active springs that move up and down and stabilize the car through the corner. I'll get to the details of why stability is important a little later in this presentation, but it's just something interesting for you to see. Then came Williams FW11B. This is regarded as one of the most successful active suspension vehicles of all time. And at this point, basically, a lot of electronic influences started coming into the cars. You had electronic stability programs. You had the ECU coming into play. You had a lot of sensors also being added to the car to aid the drivers in performing. Now, you might feel this defeats the purpose of racing, and some might argue that it does. But this is where you need to understand racing is not just about driving and being the fastest. It's also about the engineering element. What you need to keep in mind is a lot of this technology has been leaked from racing onto road cars. And that's why racing plays a really important role in the history of automotive development. Because racing cars is basically, it's like a test ground for running vehicles at a very high level of stress. So you're basically pushing that factor of safety limit. So if a car can perform in such extreme conditions, you're definitely going to be able to engineer safe components to work at road legal levels. So that's kind of a little bit about active suspension and Williams's success in that field. The Williams FW16. This car is a little sentimental. It was the car that Ayrton Senna was driving when he died. He was one of the racers in the more recent times to have succumbed to injuries during a Grand Prix. So what actually happened was he flew off one of the turns. He continued off one of the corners. He wasn't able to steer, and he went head on into the wall. What happened was a wheel and a suspension member actually hit him in the head. So at this point, a lot of changes happened in safety, and that's why I mentioned this here. Gruesome as it may be, it was a turning point for the safety point of view in the sport. They improved helmet design. They also increased the height at which the side members of the chassis are present, which are these side impact members over here. The heights were increased to prevent any intrusions from the outside of the vehicle for any sort of debris to hit the driver. Unfortunately, that was also the same weekend when we lost another driver, Roland Ratzenberger. So it was a very grim race. Now, after all of this happened, after all of the safety revolution and electronic revolution, we come to the technical modern age of F1 from the past 20 years. This is the car that dominated the first 4 or 5 years of the 2000s. This is the Ferrari F2004, which Michael Schumacher drove to win, I believe, to win his latest championship, which was his last championship, his 7th world title. And these cars were basically V10 vehicles. So they had V10 engines, very powerful. Personally, I would say these are one of the most exciting vehicles that we've seen in recent times. We move on a few years down the line. This is a Red Bull RB6. So this was the car that Sebastian Vettel drove to become the youngest world champion. Again, a rich piece of history just for you to see. That was the V8 era, by the way. And then we move on to the modern cars. So these are ones you see in races today. So this is the Mercedes W05. This was the car that won the first ever hybrid era championship. So these cars had V6, 1.6 liter V6 turbocharged engines. And this is again the phase when Mercedes has been dominating. So their engine development program was, or at least it was, leagues ahead of other teams. Now teams are catching up. But yeah, they've basically had a complete monopoly in terms of domination and scoring points in this era. Very important piece of technology. The latest change as such in F1 came in the year 2017 when all the aero regulations changed. So if you see these two cars over here, you can see that this rear wing is kind of vertical, whereas this rear wing is kind of angled backwards. These cars are a lot wider, longer, and flatter. It's literally like a plank on the road compared to this. So cars obviously got a little heavier, but they've also become a lot more stable. They're able to pull much higher Gs. Most cars can go flat out through corners that could never have been possible about 20 years back. The latest change that we see in F1 is something called the halo. There's another safety revolution 2.0. So what you see here right above the driver's head is a titanium structure. And what it does is it prevents any sort of debris, wheels, suspension elements, springs, anything that can come and hit the driver on the head. This protects them. So I hope this wasn't too boring. This is just a quick overview of the different types of vehicles that we've seen over the past few years, or actually over the past 70 years. And this is the rich history that Formula One holds with it. Okay. Before I show you any more pictures of cars, let's have a small introduction to the engineering elements. The Ferraris, I think this is Fernando Alonso's 2012 Ferrari. You can see this platypus nose over here. Very peculiar design feature the 2012 cars had. Anyways, so the first aspect of a race car, I'm not going in terms of design flow because you don't start with aerodynamics, but I'm going more in a performance flow. So these are aerodynamics. So aerodynamics is one aspect that you can work on in a vehicle. After that, you have steering and tires, which has everything to do with tire performance and how you're going to optimize vehicle yaw. So a vehicle actually yaws. What yaw basically is rotation about your vertical axis. So as a car goes through a corner, it yaws, and you quickly find out that tires are actually probably the most important aspect of a race car. So that's something for you to see. You also have the chassis and suspension. So the chassis, effectively, when you say chassis, you might think it's just the structure around the driver, and to an extent it is. More importantly, chassis is everything that's sprung. So there are two types of masses in a vehicle. There's sprung mass and unsprung mass. So basically, if you look at the vehicle and visualize the wheels to have gone off, you see that the vehicle is actually suspended in midair, and it's suspended along these linkages to the tire. So everything that's suspended is technically the chassis, apart from the engine and the aerodynamic components. So that's very important. Chassis design is something that's always improving. It's a key place to reduce weight and improve the performance of vehicles. And then obviously the suspension elements are there. Suspension has everything to do with balancing your car and balancing the loads on your tires and wheels. A very, very, very important part of cars. You have the powertrain. Of course, naturally, powertrain mainly refers to the engine and the engine intake and exhaust assemblies, and also the electronics involved in it. And the reason I've pointed over there is because the engine is placed right behind the driver in modern cars. And you see here, this is actually the inlet for the car, which is where it takes in the air, because for combustion, you need air to also go into the engine. Then you have the exhaust back here that fires out the exhaust gases. And then the final part is the drivetrain, which is basically it's like a thin line between powertrain and vehicle dynamics, because it has vehicle dynamic effects, but it is linked with the powertrain. So it's basically your gearbox, your drive shaft assembly, something called the differential, which basically distributes torque between the two wheels at the back and stabilizes the car. These are really important parts. So I'll go through it. I'll quickly go through the different subsystems that you might be interested in if at all you want to work in either Formula student, or you want to push and be a race engineer or a design engineer in motorsport. We'll start. Oh yeah, before that, one more thing. The most important thing, not the most important, but the most important for increasing performance: data acquisition and race engineering. And I'll get to this towards the end of the presentation. For steering and tires, now what I've listed as certain subjects that are relevant with this. So firstly, for understanding tires, you might think it's just pure physics. There's a lot of physics involved, yes, but it's also material science and chemistry, because you're dealing with rubbers, you're dealing with different types of tire grades, you're dealing with the tarmac, and chemistry, because I'll explain soon. So basically, you have different types of tire compounds. And what that means is the tire is either soft or hard based on the rubber composition that the tire manufacturer includes. Not to mention, it also involves thermodynamics. Now, there are two ways a tire there are two reasons why a tire maintains grip on the road. One is mechanical grip, which is basically the tire being pressed into the gravel and the small stones within the tarmac, and that kind of locks it into place. It's friction, like we learned in school about friction being rough surfaces rubbing against each other. This is basically that. But more importantly, there's actually a chemical reaction that goes on. So the tarmac actually pierces into the tire under the first layer. The inner layers are very fresh and they haven't reacted to air yet. Rubber is reactive. So when this presses in, it actually bonds with that. So there's a chemical reaction that takes place. Thermodynamics comes into play because tires depend on temperature. Tire performance depends on temperature. Generally speaking, every 10 degrees, I think the coefficient of friction increases by around 0.2, a value of 0.2, if I'm not mistaken. But there's an optimal range. If things get too hot, the tires are just going to completely glue onto the road and your performance is going to go down. Things are too cold, you're not going to have enough adhesion. So the optimal range is around 100 to 110 degrees Celsius. It's better not to go beyond 120 degrees Celsius in terms of surface temperature. Machines and mechanisms. Yep. So what you need to also know in terms of steering is steering geometries, the way in which tires work. I'll quickly go through one physics concept, which will be very helpful for you in the rest of the seminar. It's called slip angle. So when a tire is on the road, this is a tire, this is your road, and you twist it, right? When you twist the tire, there's a contact patch where basically the tire presses onto the ground. Now, if you try this, like if you're watching this webinar now, just put your hands together and then twist it this way. You'll actually feel a sort of torque or some sort of force, lateral force along the palms or wherever your contact patch is. So basically, your tire moves in one direction. It's rolling, but that contact patch points in another way. I hope you can see it here, but I've kind of made a small indentation here in the tire. So the more slip angle you generate, typically the more lateral force you generate, the better a tire performs. But a tire has a limit for slip angle. Okay, so that's also something that someone who's working in steering and tires needs to understand. This is a very basic graph. So lateral force increases till a certain slip angle. But if you basically go beyond a certain slip angle, the tire loses grip. So that's a factor to keep in mind. I hope I'm not going too fast. I have a lot of content to cover. I'm really sorry. I'll try to keep it. I won't keep it as technical as this because I hope you're not getting bored. Feel free to comment in the video if give your feedback and we'll change it accordingly. I'll try to change it now as well. So these are some of the things that tires and steering engineers work on. Some of the things you need to know if you want to work in this is CAD. So a good piece of software for CAD development. If you want open free software, you can maybe try out OpenCAD. In Formula Student, I work with SolidWorks. It's a very user-friendly software. FEA, finite element analysis. It's got everything to do with dealing with stresses and analysis. For that, we used you can either use software like ANSYS, LS-DYNA, potentially even a hypermesh. Kinematics. For kinematics is actually a really nice software if you want to visualize the way suspension elements move. There's something called VSUS. It's free, and then there's obviously Lotus Shot. So these are some of the things that you can do. Quick overview of aerodynamics. If you want to work in aerodynamics, you need to be familiar with aerospace technology. Fluid dynamics is a must. You're dealing with a fluid, air is a fluid. Now what you can see here is a graph of terminal velocity. When you start accelerating you start accelerating with your car through air or anything, if you start moving your hand through air, you can feel a force. So basically all it is a reaction force. Air molecules are hitting your hand. So the car can only go so fast. When it reaches a certain limit, it can no longer overcome the drag force that's pushing it back. That's called terminal velocity. So just to keep in mind, you make very powerful wings that can keep a car planted on the ground. Good for you, but if there's too much drag, if the car can't overcome that, it's completely useless. If you take a high-speed circuit like Monza, you don't want a lot of you need downforce. The tricky part is you need a lot of downforce in certain corners, but the payoff is that you'll have a lot of drag for the rest of the track. So there's some of the things you need to keep in mind if you're working in this field. Flow visualization. This is all about fluid dynamics. So this is a pressure distribution around the car. You need to be, so if you want to work in this field, you've got to be you've got to completely understand fluid dynamics. You should be able to visualize fluid flow around an object. So you need to familiarize yourself with fluid mechanics, a little bit of computational fluid dynamics, which is mathematics with computers, of course, to analyze fluid flow. So those are some of the things that you will experience if you work in this field. Also structural engineering. So you need to know about structural engineering and aerospace technology. This is what you see here is an airfoil, which is the most basic aerodynamic shape. You have different types. You have the most famous type is called a NACA profile, used by a lot of aircrafts and used in the space industry as well. So there's some of the stuff we'll also work on if you work in this field. Just as an add-on, this is something called an aero map. So based on how your car is angled throughout the lap, you'll have different performance benefits. If your car is angled too far in front, your front wing is going to put a lot of force, because when the front wing comes closer to the ground, it becomes more powerful. It generates more downforce. So this being wary of this map will help you understand how your car is going to behave at different angles. Then you might wonder, why would a car have an angle? Well, we'll cover that in the next section, which is chassis and suspension. So basically, chassis and suspension is all about understanding your suspended vehicle mass, which is this pink block over here, or the red part of the car, and your unsprung mass, which is everything that connects that car to the wheels, and the wheels included. Okay, so chassis and suspension engineering focuses on optimizing this set of parameters. Now, you need to be familiar with kinematics, structural engineering, and vibrations. So for those of you who are doing mechanical engineering, perhaps in your second or third year, you might be working with, you might be studying vibrations, and it's very crucial here. It's a very important factor if you want to understand not just cars, but almost everything. Almost everything has vibrations involved right now nowadays. Also, this is a subject that's important if you're interested in getting into control systems and control dynamics, because a lot of examples in that subject are based off vibrations and damping. Multi-body dynamics, again, it's a form of analyzing multiple bodies that are dynamically behaving with each other. Yeah, so this is where it's relevant. This is where the pitch is relevant. So if you can see here, the car is at a point where it's accelerating. So when you accelerate in your car, even if you sit in your car and accelerate, you get thrown backwards because of inertia of rest. But that's what happens in any situation. The whole car actually jacks backwards, and it transfers load to the back. When you hit the brakes, as you can see in this red zone over here, the car pitches forward. So when the car is in these sort of positions, you need to know how much downforce is being generated in the front of the car and the rear, because based on how much the distribution of that is, based on your aerodynamic balance, you'll have different performances. If you have too much force in the front, you're going to oversteer. If you have too much aerodynamic force in the rear of the car, you're going to understeer. Oversteer basically means you're going to spin out. So these are things that you need to look at when you work in suspension. You need to be familiar with lap time simulation. So a free software for that would be Optimum Lap, which is a free source software that you can use to do some basic analysis of laps and understand how cars go around laps. Then of course you have FEA and CAD involved in this area. So now we go to the next part, which is powertrain and drivetrain. Okay, so what you see here is an intake, which is basically, or rather, it's actually a plenum, the intake plenum. So intake basically is a subsystem, is a part of powertrain that deals with airflow into an engine. There's a lot of internal aerodynamics involved here. So it's internal CFD, CFD for internal airflow. What you need to know here is not just fluid dynamics, but also thermodynamics, because hot air is always going to be around the intake. Air that goes inside the intake and is about to enter the engine is always going to be really hot, because that engine inlet actually keeps opening between cycles. So it's going to start heating up a lot. So you need to know about materials and also thermodynamics of those materials to design an intake. You have fluid dynamics. One more thing I forgot to mention, there's also vibrations and acoustics involved, because you're basically creating a chamber in which air is oscillating. So it's very important to understand vibrations and acoustics to work on this. Fair bit of electronics, actually not fair bit, a lot of electronics involved in engines. That's probably the only place where you'll see most of the electronics of a car working. There's a wiring harness, which is basically a construction of the wires for the electronics. And it's connected to something called the ECU, which is kind of like the brain of the car. So ECU stands for electronic control unit. and it's basically the brain, the decision maker for the engine. The engine is more like the heart, it's beating, but this is making all the decisions, reading data from the sensors in the engines and telling it what to do and optimizing it. A lot of electronic influence nowadays in petrol and combustion cars. That's another factor. You also have vibrations, multi-body dynamics, again, because your engine has a lot of vibrations. You need to understand how those will affect the car. There's actually a vehicle on a dyno, which is basically a test bed for checking your engine performance, right? And then what you see here is basically the engine. We've actually removed the top of the engine. This is a KTM engine. So you'll need to understand how gearboxes work if you want to mess around with things like that. In fact, this is actually not the gearbox, it's the top part of the engine, the inlet area. But this is a chain that runs, if you see here on the right of the image, this is actually a chain that runs along the side of the engine casing. So yeah, this is what engines and drivetrain is about. I'm sorry if I can't tell a lot more about this. It's really not my forte at the moment. But I have worked a bit with intake design, so it's a great experience. If you like fluid dynamics, then it's either intake design, exhaust design, or aerodynamics that you really need to involve yourself in. Again, you work on various other aspects like lap time simulation, engine modeling. You can use software like Ricardo for doing the flow, and also I believe GT Suite can be used for simulating engine performance. Then you have ECU, different ECU and DAQ softwares to understand how all of this comes into play. Now, we'll go into data acquisition and race engineering. And this is kind of my specialty. This is what I worked on in my thesis. And from driving the vehicles, I kind of had an idea of how to read this data in Formula Student. So it was a great experience. This is hardcore race engineering. This is where you start understanding how to simulate the vehicle and how to create strategies and how to basically make your car perform and beat the car next to you. And that's what makes this field so exciting. If you're really into designing and you're really innovative and you like designing, all the other designing aspects are for you. But if you're more interested in the race strategy and the way in which you can make a car really really destroy your competition, metaphorically, this is where you want to work. So you need to know about everything. You need to understand vehicle dynamics, aerodynamics, powertrain. The cool part is you need to understand, at least, if not how to design, at least how they all work together. It's a very wholesome part of the car. It's like the last step to victory, and almost just as important as every other step that leads to it. Now you need to you'll be working a lot with data analysis if you get into this field, analyzing data. So if you like graphs, if you really like interpreting graphs, this is the place to be. You need to have reasonable driving and racing acumen. Not completely necessary, especially if you're working in commercial vehicles. As long as you know about performance, it's fine. But if you really want to engineer a driver, you need to kind of understand how to drive yourself. So it's about understanding different racing lines. It's about completely involving yourself in the process of racing. So that is there. If not in real life, of course, virtually there are so many ways you can really learn that. You'll be working with mathematics, statistics, a lot of colors. If you like a lot of colors, it's either lapse time simulation or FEA or CFD. These are places where you see a lot of graphical elements for understanding your data. So that is a mathematical modeling and simulation. Basically, it's about knowing how to construct a vehicle or construct parts of a vehicle virtually as a simulation on its own. And it's something you need to familiarize yourself with if you really want to work in the development of simulation software. Another thing, race strategy. When you get hardcore into race engineering, it's about understanding strategy, making decisions on the fly. Now, almost all racing series have pit stops involved, which is basically because you're going to run out of either fuel in certain series, or your tires are going to shred off over time. So for these two reasons, you need to go into the pits, unless of course you have other mechanical issues or even a driving penalty. But it's all about understanding how your competitors are going to race against you. A very interesting factor that affects all of this is something called a safety car. So usually in racing series, when there's an accident, something called a safety car or a pace car comes out. And what that does is it slows the field down and bunches it together, so that when the entire field of cars is at one part of the racetrack, the marshals and track workers can come and clean off the debris. And it also slows down the track, just so that if a driver is stranded on the road, they can get out safe. Now, safety cars play a very important role, and I'll kind of give you an example of that a little, maybe after a few minutes. Some of the software you need to work on in this field: lap time simulation, very, very important. It's all about, it's not only about simulation, but it plays a crucial role. Only it's lap time simulation will only give you as good an output as the inputs you give into it. So if you put rubbish inputs into it, you're going to get bad inputs out. So it's all about putting the right inputs, technically and physically using the most appropriate and sensible inputs for your car. Data acquisition, not just in terms of software. So this is basically a screenshot of Motec software, which is used to read data. But data acquisition also involves using the data acquisition logger, which are devices that actually take in all of this data from sensors. So it does involve a bit of electronics if you want to get into that part of it. Matrix-based calculation, vehicle modeling. What I'm referring to here is MATLAB and Simulink. Those are very popular pieces of software that are used for simulation. But if you want to try out a software that's more open source, there's something else called GNU or Octave, which can be used for practicing and messing around with the software. I'm pretty sure it can also be used for for reasonably high performance tasks as well. So those are some things for you to remember. Right. So this is an example of data acquisition for a car around Le Mans circuit, the Le Mans circuit. I've blackened out few pieces of data that are not relevant. I've just hidden them. Oh, wow, I ruined the surprise. Yeah. So these are some of the channels you can look at. You have so there's actually a comparison between two laps. What I've done here is I worked with my classmates as a side project, and we did a race setup and a qualifying setup for a car around Le Mans. So this is basically a comparison between those two cars, and you can look at different ways in which the car is behaving. There's something called tire saturation. In simple terms, it's how much of the tire performance is being used. If it's 90% saturated, 90% of its grip is being used. Once you reach over 100, 110% saturation, you really start losing control. Obviously, when you go over 100, the tire starts sliding, but it's still controllable. So these are some of the channels. You have steering inputs here. Generally, it's not the best way to look at it because it only shows you the exact steering position at a point, but it can be used for visual purposes. This is a GG diagram, a G-force Y, rather G-force Y and G-force X. And actually, it's better not look at it as Y and X. Look at it as lateral and longitudinal because the SAE axis is flipped. So what this basically shows is how much of the car is performing around the outer limits. So you see the outer limits of the GG diagram here. That shows you that if there are more points on the outer limit, it's a good thing because that means the driver is pushing the car to greater limits. Sometimes you have GEG diagrams that'll kind of be like this and then cut off over here. It doesn't mean it's a bad driver, and it doesn't mean it's a very good driver either. It all depends on the track. It depends on how many corners are actually pulling that side of the G-force. If you're taking a left side corner, you want to look at that end. Right side, you look at the other end. So this is a very interesting piece of software. This is a very interesting plot. If you use it the right way, it can be very meaningful from in terms of values. But generally, it's good to just look at it from a subjective point of view. Then you have other channels. This is a speed plot of the car, how the car is speeding through corners, slip angles. Again, tire slip, how much the slip is there. This is an aero map, shows you a bit of aero performance, sort of like what I showed before with the oval shape on the colorful graph. This is basically that without the color. So yeah, those are some of the elements of race engineering. I would love to show a lot more, but we're kind of strapped for time. I really wanted to show you this section, so let me try to show it as quickly as I can, as detailed as possible. Classification of four-wheel racing. So if you're really interested in racing, you'll like this section. If you want to start watching racing, you'll still like this section because it gives you a good idea of what it is you might like to start, what you would like to sample first. Racing, kind of what happens is you start watching one series and you kind of get attracted to other ones. This gives you a good starting spot. Now, four-wheel racing is broadly classified to open-wheeled cars, formula cars like Formula One, where the wheels are open. Old Formula One cars were closed, but the recent formula is open wheels, closed-wheeled cockpits, sports cars basically. In open-wheel cars, you have American series, Skip Barber. Skip Barber is a racing school. in America, which teaches people to drive. So what you see here is the Mazda RX-8. It's just a practice car going around a skid pad. And it's not an open wheel car, but it's a training car used for that school. IndyCar, which is one of the highest forms of open wheel racing in America. These cars are famous for the Indy 500, which I believe the Indy 500 is this weekend or the next. So it's a very big event, very, very important in motorsport. So this is actually a one make series, as in the chassis is designed by a company called Vellore. And these are basically 2.2 liter V6 engines, and then they have even aero kits that are specifically manufactured. So either Chevrolet or Honda, both those companies design aero kits for vehicles for the teams, and they can buy either one. And I believe they can change a few things in it. Then you have the Asian side of things. So you have one make series, especially in India. So you have the JK Tire series, and also importantly the MRF racing. In terms of the way we see progression, a lot of people go through MRF. JK Tire is more, it's not actually only restricted to India, it also works in other parts of Asia as well. So that's really good for that type of international exposure. You have a lot of Indian racers have gone through MRF racing. So you have MRF 2000, which are basically use 2-liter Renault engines, and then you have the MRF 1600, which is the 1.6-liter Ford engines. And then we go to the pinnacle of Asian motorsport, and that's in Japan. It's called the Japanese Super Formula. These cars are actually sometimes faster than F1 cars in certain situations. I don't believe it's still the case in the modern era, in this new hybrid era, but there was a time in the 2000s where they were faster in certain circuits. Very interesting. They also have common Dallara chassis. They have about 540 horsepower outputs, weigh about 670 kgs. It's a very good power to weight distribution. Now we go to the European series. So you have junior regional series, something called Formula 4 and Formula 1000. I'm not sure much about Formula 1000, but it is there. Formula 4 is more well known. So you have specific series in Italy and in England, and a few other places as well. So this is basically a British Formula 4 car, and what they use is a 1.6-liter Ford engine for the one make chassis. Internationally, you have Formula BMW, but this was the series that Sebastian Vettel came from. So he really made a mark in motorsport from there. You also have Formula Renault, which is more popular. Formula Renault, they use 3.5-liter V8 engines. So it's quite interesting if you want to watch junior racing. Good thing about junior racing series is stakes are high, of course, but since they're all junior drivers, they tend to be more aggressive, and the racing is a lot more risky. Not in a dangerous way, but more in terms of excitement. So it's a lot of fun to watch your favorite drivers go through junior series and reach F1 ultimately. Then, of course, you have the pinnacle, the international group. You have Formula 3 over here, Formula 2, Formula 1. You see the way they've evolved over. You can see the comparison basically. Formula 1 cars are huge. Formula 3, generally they're small, and their engines are also really small. They're kind of like junior versions of Formula 2 and Formula 1. Then you have Formula E, which is kind of the next step in racing. Everything in the world is going electric. We're going to run out of fuel soon. Environment's also in danger, so you need to think of ways to make automobiles and racing more sustainable. So Formula E is a great initiative. Started quite a few years back, and now they're in the second generation of Formula E cars. So that's something really interesting. Go on to closed wheel racing. NASCAR. This is one series that I've been really attached to for a long time. And these cars go in ovals. Basically, they mostly go in ovals. So they like a train of cars that go around. But you also do have circuits at times. These are stock cars, which means that they have they're kind of the same chassis. They're made directly by the manufacturer, but then they kind of stripped apart and then they add a roll cage and then develop the bodyworks. This right here, if believe it or not, is actually the Chevy Camaro ZL1. I think it's from 2019, and these are mostly V8 5.8 liter V8 engines. So these cars generally go in a train, in a series, and they draft each other and use aerodynamics and pass each other. And it's more of a sport of aerodynamics and engine power. Very risky, a lot of fun. It's very different. So it's something for you to also check out. But it's really fun to watch. We have off-road series like WRC, the World Rally Championship. And then you have WRX, the World Rally Cross Championship. So World Rally Championship, WRC goes only mostly on dirt tracks, snow tracks. WRX goes on hybrid tracks, dirt, snow, tarmac, everything is kind of mixed up. WRX cars are a lot bigger. They're bigger variants. For example, WRC kind of runs might run the Polo R, whereas the WRX might run another version of Volkswagen, maybe another hatchback from Volkswagen, but a bigger variant. And WRX is a lot more aggressive in terms of contact. Very, very exciting. The dynamics of off-road vehicles are very complex. Something really interesting to look into. Circuit-based, you have touring cars, basic cars. So you have grand touring cars, like the really cool sports cars like Ferraris and the Lamborghinis. But then you have touring cars, which are slightly lower variants, but still really good. For example, I believe this one was BMW. They run things like BMW M3s and those sort of vehicles. So it's very cool as well. It's a junior series, of course, but people who are getting into sports car racing and want to go for the next stage I'm showing here, they usually go through touring cars. Sports cars, we have Americans, the American side, which has IMSA, which is the Middle International Motorsport Association, International Motoring Association, I think. And basically what they do is they have different cars running at the same time. You have GT cars, you have these specific different looking cars called LMP1 cars. They all run at the same time. This is an endurance series. Most of those races last for almost, they go from anywhere between 3 to 6 to even 12 or 24-hour races. The most famous one in IMSA is basically a 24-hour Daytona race series. Then you have international. When you go to international, you have the WEC series, the World Endurance Championship, which is kind of similar to IMSA, but it's a different, there's slightly different regulations. And sometimes WEC cars also take part, I think, in the Daytona series. And WEC is what hosts the Le Mans series, and some IMSA cars also take part in that. So it's really cool. It's a lot of fun. If you don't know which type of car to look at, go for one of these two series. Start looking at those. It'll blow your mind. It's really well. You rarely see series where you have different types of cars running at the same time. So this will really spark your interest if you want that. Okay, we have like around 5 minutes left. So I'll go through a small session on race engineering or whatever I can. These are just references for the images. Okay, so how do you start setting up your vehicle? You want to set up your weight distribution. You want to know how much weight is in the front, how much is at the back. You put too much weight at the back, your car will spin out easily. Put it too much at the front, you'll go off course. And I'm sorry, I'm not being very technical now. I'm just strapped for time. In the question answer session, we could be a little more technical if you want. That gives basic mechanical stiffness and balance. Then you have wing angles and ride heights. That sets up how your aerodynamics will work. After that, you move on to springs, which kind of link aerodynamics and the mechanical end of the car. So aerodynamic balance is when you have high speed corners mostly. Mechanical balance is the weight distribution front to rear. It's more important for slightly slower speed corners. And I'll show you in the next part. Anti-roll bars, camber and toe, all of these make up mechanical balance. You have the differential, which kind of controls your torque output at the back of the car. So it either stabilizes or destabilizes the rear end of the car. So that's important in mechanical terms. You finally have gear ratios, final drive ratio to finish up powertrain. Most of the powertrain ends of things. A lot of things on engines are actually done in the design phase. As far as I know, these are most of the things you can do from a race engineering perspective, and also perhaps tune your ECU. There may be other things that I'm not aware of that you can also work on in the engine. Maybe I'm missing something very, very obvious, but at the top of my head, I'm not able to think of it. So this is just an overview. So let's say you have this track. This is the Le Mans track. It's quite a long circuit. Really, really fast cars at the level of Formula One cars also take around 3.5 minutes to complete this. So it's a big track. So let's see, how would we analyze this track? Well, obviously, to analyze a track you've never seen before is a little difficult. So it's always good to see a reference or at least a simulation. Generally, when new tracks come into race calendars, engineers simulate it with their simulated. They use a model version of their car and then simulate it. So here you have this track. I already know quite a bit about this track, so I'll show you how I would go about it. So first thing I'll say is how many straights are there? Well, you have one straight section over here, one over here, one right after that chicane, one leading down to towards the end of the second sector, one just at the beginning of the third sector, and That's about it, right? So this tells me that there are a lot of straight sections. Do I want a car with really big wing? Do I need a car that has very angled wings? Probably not, but I need to think, I need to look at the other parts of the track before fully understanding that. So let's look at this next part. This is a Dunlop curve. It's the first corner, quite high speed, not very sharp, but it still puts a lot of load on the tires. That's why it's a high energy corner, high energy for tires. So I've put that as an orange color. Next, the Tetra Rouge corner, which leads on to the back straight. Again, very high speed. It actually goes really fast. I have a video to show it, but it might lag a bit, which is why I'm not showing it at the moment. If we have time, I'll show you a lap around it. And then we get into this final sector. So we go all around the track, go all the way around here, and then we finally reach this part. High speed flowing corners, the Porsche curves, perhaps one of the most famous sequence of corners in motorsport. Very, very important to set up your car going through this, because it's actually very tight. There is some runoff area, but there are also walls. You mess up over there, you crash. A year of preparation for the biggest sporting event, for the biggest motorsport event in the world, is going to go down the drain. So you have to be really careful, make a car that goes through that properly. So now we reach a conundrum, we reach a problem, or rather it's sort of like an impasse, and we need to find a solution. The Porsche curves need a lot of aerodynamics. Tetra Rouge, which is this corner over here, needs a good aero kit. But you also have straight sections at the back. Cars that have something called DRS can open the rear wing electronically and reduce drag in these sections. They don't have to worry. But if it were me and I'm making it for a sports car, I would be a little concerned about these sections. An ideal way to go about this track would probably be to go with a medium aero kit to have a good balance. When I did my project, when I did my MSc thesis, I actually created a method to calculate how much time a car spends in different types of track sections, and I used that to generate an algorithm, and it told me the best trade-off. So you can sit and create things like that with Microsoft Excel to better understand it. Next, these are the chicanes of the track. That's where you need a lot of mechanical balance. To get through that properly, you need an oversteering car, a very agile car, but not something too much so as to spin the car out. And then you have corners that don't play a very big role. These are quite slow, easy to take, just get through them safely type corners. Okay. Next, heavy braking zones. See the heavy braking zones that are popping up over here at the back straight. You also have a heavy braking zone into this section. And the final part for tuning the differential, you need to look at these low traction zones. Low traction, that's why I've put like a slippery sign. Low traction, you're accelerating out of a slow corner. You spin the wheels too much at the back, your car spins out. So something else for you to look at. Low traction here, low traction here, low traction here. So looking at all those things, that's how you would probably analyze a track. And if you go through all of it sequentially, do it a little more smartly, and take time to put values and stuff. This I've rushed through it, but if you put values and stuff, you get an overall solid overview of the track. Then you can really start setting up your vehicle. Then you start talking to the driver. There's no such thing as a perfect setup for a track. It all depends on whether your driver can reach it. Something we all forget is it also depends on the reaction time of a driver. You can make a car that's very agile. In fact, a very agile car is the best type of car. But if a driver can't cope with that, he'll end up spinning it out and being slow. So it's all about understanding your driver too. It's just as much psychology as it is engineering. I hope it's psychology, yeah. But it's not just engineering is what I'm saying. You need to really love and involve yourself in the sport, understand drivers to really be involved in this section. So just as an overview, these are some parts of the Le Mans circuit. You see the first set of corners here. You go flying down here. You can see how the aero balance and mechanical balance changes. You can see tire, how the tire saturation changes. You see spikes. The tire saturation goes up too much, you'll start losing end on that end of the car, losing grip. I'll just flow through this quickly. You can maybe have a look at the recorded session a little later to try to understand the graphs. I'm just showing this so you can have a look at it now. A lot of changes in understeer and oversteer. You have big issues in balance here. And these three zones are basically these three chicane areas here and the final turn. So you see, whenever you're on a straight or in a high speed corner, you don't have a lot of problems. When you get to these slow speed twitchy sections, right, your car starts twitching. And then again, you have corners here. You can see over here how the driver is pressing the brakes as he enters the chicanes. So you see here, the throttle, the way the driver, if you look really closely, you can see the driver blipping the throttle over here because he's trying to control the wheel spin at the rear end. And you go on to the next section. This is kind of straightforward, nothing much to really see here. You see how the driver inputs the steering and the throttle as he goes through that section. You go through the final section, high speed Porsche curves. You see how much it's like vibrating over here, and we actually set this up to be an understeering section. We set up the car to understeer through the section because it's a lot more stable. These corners don't require too much movement, but at the same time, you don't want something that steers like a brick. Like you don't want it to be really sluggish. So we had to get a good trade-off. I've blocked out the values here, but they're the reasonable values that we used. And yeah, that is basically the end of that section. So this is kind of how you would analyze the racetrack. I'm sorry I rushed through this. But yeah, I tried to explain as much as I could. Unfortunately, we are out of time. It's almost 6 o'clock now. So with that, I'd like to thank you for your time. Thank you for listening. I know it was a little rushed, but I really hope this was, we really hope this has been quite informative for you all. And let us know in the comments. Let us know. Give us feedback. We'll be more than happy to improve for future sessions if at all we can. And we're now open to any questions. Feel free to type in your questions in the comment section below, and we will try to cover as many as we can, and as long as time permits. Thank you.
Can you give a bit brief about your journey from, after completing BTech to masters?
Okay. um, yeah, so I finished BTech in 2018. So by that point, I'd worked quite a lot in Formula Student, and it. Trust me when I tell you, it's addicting. It's a lot of fun. It's an addictive place to be. Once you join it, if you guys are in their early stages of university, or even if you're in third or fourth year, if your teams permit, be involved in that because that really inspires you. So for me, it was a lot of fun working in the team. I'm very proud of everything I was able to accomplish and work on during that time. And it's got to be one of the most wholesome engineering experiences. Actually, one of the most wholesome academic experiences I've ever had in my life. And that really inspired me. So that's kind of what pushed me into doing a master's in motorsport engineering. And that was kind of the flow into it. So I started my course in Oxford Brookes University in September 2018. Um, it was mind blowing. Okay, I went there to learn everything I can from a technical end about racing. Racing, something that I've loved ever since I was 5 years old, and that really, it met all my requirements, and it provided more than I could ever ask for. It was entirely focused on understanding race cars. Now, obviously, we had subjects that were linked with automotive. Like we had classes with the masters in automotive students. We had classes in on vehicle dynamics. We also had an option to take either data acquisition or electric vehicles. There were common subjects, but they were kind of all oriented towards racing. I remember our vehicle dynamics course was also heavily focused on performance engineering, performance improvements. We had brilliant faculty who have worked, professors who have done research, who have worked in motorsport, who are consulting from motorsport. It was a great experience. The second half was mostly race engineering oriented, a little bit of crash impact analysis, a lot of FEA involved in that. But yeah, I really wanted to do that course, and I wanted to do a thesis based on racing, something technical based on racing. So given the option between design oriented theses and more analysis oriented theses, I went for race engineering based. So that was kind of my story, and it's been surreal. I learned a lot. It was great.
Yeah, thank you, thank you. Another question is there. What were the softwares that you recommended? Optimum Lab and other one. If you can just
Yeah,
brief it, rename, yeah, repeat it.
yeah, I'll repeat that. So yeah, we'll start off with kinematics. It's about like understanding the way your linkages move, the way your camber changes, and how your tires behave. It's a lot of machines and mechanisms. So for that, a good software is, I mean, it's not a software. It's actually a web-based application called VSUSP. I think it's free to use. It's really good to familiarize yourself with suspension movement. So you keep that one in mind. I think for paid software, I think there's a software called Lotus Shark, which can be used. Um, it's more of paid stuff. If you go to CAD, I think Open Freeware, you have OpenCAD, which is a good way to understand the way in which CAD modeling works. And as a paid software, we use SolidWorks in our teams. Um, SolidWorks CATIA is also a good place, more industry oriented. Computational fluid dynamics. So I think for CFD you can check out SimScale, which is quite easy to use. You don't need a lot of system power for that because it's mostly cloud computing. It's cloud based. The simulations are done. You can check that out. Then obviously there is more high end software like Star CCM Plus, which we used in our masters for a more high end analysis. What else? FEA, we use ANSYS. ANSYS is a good place to start. If you, those of you who are still in university, most universities will have access to most of these software. So if you're allowed to, go to your labs and check them out, as long as you have access to the license, use it. Um, yeah, and that's about it. And then you have LS-DYNA and HyperWorks as well for that. Lap time simulation, check out Optimum Lap. It's a good place to start. More high-end application, I used something called AVL VSM during my time in MSE, but it's more for professional companies. It's not something that might be accessible for you at the moment. And that's about it. Wiring, I think electrical and wiring, I remember using a software called Eagle, but this was a long time back in 2014. So I think someone who's more familiar with electricals, one of your friends might be able to help you on that. Yeah.
Yeah,
So I'll move forward.
then we have
Yeah.
another question. How racing slick tires are superior over road tires?
So racing slick tires have a really good contact patch. They have maximum contact patch, which means so in your road tires you basically have grooves in it, right? That's called tread. The reason we have that is because it's kind of a all-purpose weather tire. Like if you go on a dusty surface, you're going to go on even normal roads, and especially in India, roads are a bit more dusty. It's a tropical area, so there's a lot more dust. So it really makes no sense to have a tire that has it is completely flat, and most parts of the world have a lot of dust. That's why we have that. When it rains also, basically the treads in road tires, they create channels for water to flow through. So instead of the tire creating some sort of water barrier between the rubber of the tire and the surface of the road, and by the way, if that happens, the car will start sliding. It's called aquaplaning. So you don't want these sort of things, and that's basically why we have grooves in the road tires. That's one difference. The second difference is the construction of the tire itself. So road tires are give a lot more feedback to the driver. Like they know the driver can feel whether the tire actually is about to lose grip. Racing tires are not like that. They have a much higher limit before they lose grip, but they lose grip instantly based on the construction of the tires. That's something for you to go and check out. Check out the construction between road and racing tires, and you'll understand exactly how the physics of that works. I think the third point is probably the compound used in racing slicks. They're much more sticky, they're softer, they have much stronger chemical reactions, and more importantly, they're much fresher than road tires. Like racing tires, you use them and then you dispose them. That's how they are. So these are some of the main differences.
Yeah, the last question, how to become a race engineer? Okay, and you can jointly answer this question. Like some other person has asked this question. How to join Formula student? As I completed my graduation in mechanical engineering, but my college was not having any connection with Formula student or Formula career or something like that.
Mhm.
You can jointly answer these two things. Then we can complete the session.
So, I don't really think there's any straightforward way to become a race engineer, because in order to really work properly in race engineering, you need to somehow show that you have really understood the car. So unless you have some sort of experience of working on cars or looking at the electronics and understanding data, it's not as simple as just going towards race engineering. If you're really interested in that, and trust me, I'm actually in the same process. So it's interesting that you ask that. Try familiarizing yourself. If you're interested in race engineering, that means you naturally are interested in racing. So understand the ways in which race cars, the way in which race cars work. Uh, I mean, like if you see on the screen, I'm making a small series as well on my channel. It's maybe just an intro series for you to understand. Like some of the stuff I've covered in this session, I'll explain it in a little more detail in those series, those videos if you're interested. But yeah, just start reading more about race cars, read about vehicle dynamics, understand it inside out. Uh, and again, also be involved in Formula Student when it comes to that question. Again, it's unfortunate if you weren't able to get the opportunity to work on it at that moment. But a way to be involved in Formula Student is probably through volunteering. And generally, I know for a fact that the Indian events require volunteers as design judges, and they like people who have industry experience. So if you're already working, or you've been placed, or you're working in an industry, or at least you're involved with some company, that adds to your experience. Getting involved in Formula Student can give you a lot of contacts as well. It helps you network more than anything, because you'll meet people from the industry. Unfortunately, I can't give you any straightforward answer as to how to reach F1 or how to be a race engineer, because there is really no defined path. It is circumstantial. It depends on who you network with, how you project your expertise, and yeah. If any of you are planning to go for masters and stuff, definitely, if you're looking at masters in international universities, a lot of them do have Formula Student teams, and nowadays a lot of Indian colleges, universities also have it. So if some of your viewers here are maybe in 12th standard or so, make try to get yourself involved. It doesn't have to be Formula Student. They have Baja, they have Formula Hybrid, and then it doesn't necessarily have to be race cars. You can hone your skills in copter research, copter development. There are robotics teams as well, autonomous vehicles. There are so many ways to do it. I'm really sorry I can't give you a straightforward answer, because it is a very broad spectrum. But how to be a race engineer? Start watch a lot of racing, get familiarize yourself with racing, and learn vehicle dynamics, learn how to understand a car. And then if you need more guidance, feel free to connect with me, and I'll be glad to help you out more.
All right. Thanks a lot, Saidat, for your time and your inputs. So we really enjoyed a lot. Thanks a lot. And with this note, we can complete today's session.
So
Thank you.
absolutely, thank you very much. Thank you.
Thank
Take
you
care.
all. Yeah. Have a good evening.